Now we've looked at transformations of adding or multiplying a constant to the function, the a and the d transformations, and we looked at adding a constant to the variable inside the function. The last transformation will be what happens when we multiply a constant to the variable inside the function. For our first example, we'll look at 2x squared. So we found the x inside the function and multiplied by 2. Let's look at the table of ordered pairs. Now if x equals -2, 2 times -2 is -4, and then that value squared, positive 16. And the rest of the values that way. Now we can see some sort of multiplicative result, but don't focus on that right now because we're not looking at multiplying a number to the result of the function. We're focusing on what happens when we multiply a number to the variable. So let's look at the graph. Here is x squared, and here is the graph of 2x squared. Now again, ignore the similarity to the vertical stretch because I want you to see that each point horizontally, because if we're working a transformation on the variable, it's some sort of horizontal change. Multiplying by 2 has pulled each of these points back closer to the y-axis by a factor of 1/2, 1 over 2. So the point at 1, 1 has been pulled back, squeezed closer to the y-axis by half, from 1 to 1/2. The point that was at 2, 4 has been cut back to 1, 4. Its horizontal value has been cut by a factor of 1/2. Let's quickly look at a couple of others. If we see 3x squared, now every point is now a third of its horizontal distance. The point at 1, 1 is now at 1, 1/3. From 2 being scaled back to 2/3. Every horizontal distance is now 1/3 of what it used to be. And here's 4x squared. Now every point horizontally is 1/4 of its original value. From 2, 4 back to 1/2, 4. Cut into a fourth, from 2 down to 1/2. Let's look at our other function, 1 over 2x. We found the x inside the function and we are multiplying by 2, and we get these ordered pair solutions. When x is -2, 2 times -2 becomes 1 over -4, -1/4, and so on. X is 0, we still have an undefined expression 1 over 0. Here's our original base graph, and now here's 1 over 2x. Things have been squeezed closer to the y-axis by a half. So from 1, 1 back to 1/2, 1. And from the point here at 1/2, squeezed, cut in half down to 1/4. Here was our point 2, 1. Now it's been cut in half down to 1, 1. So multiplying the variable times 2 seems to actually do a compress. And again, with horizontal change, we see an effect that is opposite of what we see, because we're not actually changing the function value this time. We're actually kind of changing the scale. We're changing this coordinate plane. We're actually stretching it out. The axis stretched out by a factor of 2, and the result is that the graph seems to be smaller. So multiplying by 2 is actually horizontally compressing this graph by a factor of 1/2, 1 over 2, the reciprocal of this constant. Let's quickly look at a couple of other ones. 1 over 3x, 1 over 4x. We're seeing it more and more squeezed horizontally toward the y-axis. So we'll represent this transformation this way by saying we're multiplying a constant to the variable, times b, right inside the function. And we see a horizontal compress when b is a number greater than 1. We saw when we did times 2, it got compressed closer to the y-axis by a factor of 1 over 2. When we did times 3, it was squeezed closer to the y-axis by a factor of 1 over 3. Let's look at when we multiply by some fractions. So we'll choose 1/2 times x inside the function. We see these ordered pair results. When x is -2, we multiply by a half, so we're down to -1, and -1 squared is +1, and we get the rest of these results. 1, so 1/2 of 1 is a half, and then 1/2 squared is 1/4. Let's take a look at the graph. Base function, x squared, and now 1/2 x, that quantity squared. And here's 1/3 and 1/4. As we multiply the variable by a fraction, it actually stretches this graph out horizontally. So the point at 1, 1 has now been stretched out to 4, 1. The point at 2, 4 has been stretched out to 8, 4. each x coordinate multiplied by 4. So we see the opposite sort of effect of what we would expect. Multiplying by a fraction 1/4 is actually stretching it horizontally by a factor of 4. So let's look at our other function. I'm finding the x and multiplying by 1/2, and again I would probably simplify this fraction, but I'll keep it like this so we can clearly see we're taking the x times 1/2 inside the function. We'll get these function results. If x is -2, we have 1/2 times -2 is -1, and 1 over -1 is -1. If x is 0, we still have a 0 in the denominator undefined. Let's take a look at the graph. Here's our base function 1 over x and 1 over 1/2 x. We're stretching it out horizontally away from the y-axis. The right is being stretched more to the right. The left is being stretched more to the left. And it's being stretched by a factor of 2, the reciprocal of this constant. So these transformations that are on x, here we see a 1/3 being stretched horizontally by a factor of 3, are working opposite of what we kind of expect from what we see. And it's because we are operating on the variable, not on the result of the function. So the a and the d transformations, which operate on the function, either adding or multiply, they work just like we would expect. If we add a number, it goes up. The graph goes up. If we subtract a number, the graph goes down. If we multiply by a number like 2 or 3 or 4 or bigger, we stretch this graph out vertically. And if we multiply by fractions like a half, a third, a fourth, we squeeze it by those factors. But the opposite happens with the horizontal changes, these transformations that are applied directly to the variable inside the function. We saw adding 2 made it shift to the left. Subtracting 3 made it shift to the right. And here we see something similar with the opposites. When we multiply the variable by a third, we're actually stretching it out horizontally by a factor of 3. Let's see a few more quick ones. Here's 1 over 1/4 x, 1 over 1/5 x. So we keep seeing it being stretched more and more horizontally. 5 times as much now. What was here horizontally at 1 has now been stretched out to 5. What was here at 1/2 has been multiplied by 5 to 2.5. The 1/3 times 5 to 5/3, 1 and 2/3. So every point horizontally multiplied by 5. So we'll sum up the results here. A horizontal stretch when we multiply by a fraction. And it really deep down has to do with, since we're multiplying directly to the variable before we do the function, the reciprocal or the exponent of 2, the change is really happening to our frame of reference. We're stretching the axes, the coordinate plane out, or compressing it. And when we multiply by a fraction, we are condensing the coordinate plane. And the visual result is that the graph appears to be larger, the horizontal stretch. And when we do b is greater than 1, we're actually stretching out that coordinate plane. And as a result of stretching out those axes, the graph that was there appears to be smaller. And that's why it appears to us as a horizontal compress in that scenario. So let's hit the last one when we use multiplying by a negative. In this graph, we get very similar results because it's happening inside the exponent of 2. So when we have x equals -2, opposite of -2 is +2, which is 4. But whether we're putting in a negative or a positive, we get a positive result. So we actually get an exact identical graph. Let's go over to the other function and say what happens when we make this x negative. Well, it changes the sign of our function results. If x is -2, now we have opposite of -2 is a +2. So 1 over +2 is this +1/2, and that's how we'll get the rest of these function values. Let's take a look at the graphs. The base function x squared and our new function negative x squared, well, we saw in the table of ordered pairs it was identical, and we get the exact same graph. But what's happening is a horizontal change, and it's a reflection. How we saw changing the sign made some sort of reflection. Now when we're making a change in sign to the variable x, we are doing a horizontal reflection, reflecting about the y-axis. So since this figure, this parabola, was symmetric about the y-axis, this new graph looks exactly the same. But we'll be able to see some differences with the reciprocal function, 1 over x, And now let's look at 1 over negative x. So horizontally, the points have been reflected about the y-axis. What was here with positive 1/2 2 is now at negative 1/2 2. And where we had negative x values, they've been reflected over to become positive x values. This is a tricky one to see, usually because algebraically, when we put a negative on the variable x, we can do some simplifying to make it appear like some other transformation. And that's the direction that we're headed to next, where we explore how some of these different transformations actually make very similar results. But for now, I want you to keep in mind that when we make changes to the variable x, it is some sort of horizontal change. And when we flip the sign of x, we reflect it horizontally. We reflect it about the y-axis. So we can sum up that last observation by saying that when we are dealing with a negative value of b, we must also reflect the points on the y-axis. The graph itself will be reflected about the y-axis.